become plutonium-239. All right, I think that sort of explains itself. Well, that's about what we need to know about nuclear fission. And before I close this lesson, let me spend a couple of minutes talking about nuclear fusion. Well, nuclear fusion is still not a means of producing nuclear energy yet, and therefore we will not be spending a lot of time on it. Nuclear fusion is the energy producing process which takes place continuously in the sun and in the stars. You see, in the formation of a star, if you know the history of the formation of birth of a star, now how does a star take birth? The nebula, the space between stars and galaxies, are filled with all kinds of gaseous particles. Any disturbance anywhere, any part of the universe, like a supernova for example, can create an instability. And that instability will bring these particles together by force of gravity. And eventually, after millions of years, the gravity pulls all these particles together, creating great pressure and temperature. A stage will come when the pressure and temperature inside is so tremendous that this gas inside is no longer the normal form, but they are plasma. The electrons are stripped off the atoms, and these nuclei, well, mainly hydrogen, the nuclei will be traveling with tremendous speed, and they hit against each other and fuse to become deuterium, and then deuterium and deuterium will fuse to become helium. So this is the process of a star formation. But in order for this to happen, the temperature must be of the order of about 15 million degrees Celsius. Now, temperatures below that cannot start a nuclear fusion. In the core of the sun, at temperatures of 10 to 15 million degrees Celsius, hydrogen is converted to helium, providing enough energy to sustain the life on Earth. In fact, all that energy that we get from the sun is the byproduct of this nuclear fusion. So fusion can produce tremendous amount of energy. So this is what happens. A deuterium fusing with a tritium produces a helium nucleus, a neutron, and tremendous amount of energy. So what are the required materials to start a fusion reaction? You need deuterium and tritium. Well, deuterium is a proton and a neutron. Tritium is a proton and two neutrons. Combined, you have a nucleus of helium, two protons and two neutrons, and of course a free neutron comes out of it. Now, most suitable reaction occurs between nuclei of these deuterium and tritium. Now, at the temperatures required for deuterium-tritium fusion, over 15 million degrees Celsius, the fuel has actually changed from gas. The hydrogen has changed from the gaseous state into the plasma state. And in the plasma state, actually the electrons are stripped off. And in order to produce nuclear fusion, we need to create that kind of a temperature on the surface of the Earth. Now, is that possible? Well, there is possibility. If you want to create a fusion bomb, a hydrogen bomb, the trigger for that will be a fission bomb. So a fission bomb exploding will create the necessary temperature condition to activate fusion. And that's the reason why a hydrogen bomb, in fact, America has a stockpile of large number of these hydrogen bombs where fusion energy is used to produce large amounts of energy. And the trigger of that is a fission bomb to create that kind of energy. In order to use that in a reactor, it is not possible. It's not a feasible thing. And that is why we are unable to use or harness the fusion energy for producing reaction. Now, seawater contains an abundance of deuterium. And tritium is part of it's rather difficult to find tritium. So if you want to produce nuclear fusion, the required fuel will be deuterium and tritium. Deuterium can be found abundantly in seawater, but tritium cannot be found as much. Now, there is no sizable natural source since tritium is radioactive with a half-life of about 10 years. Now, it can be obtained by breeding the tritium from lithium. It is possible to create that. Now, some advantages of fusion reaction are, what are some of the advantages? It's a vast new source of energy. The energy released in fusion is much, much greater than energy released in fission. So it's a very big source of energy if we can harness it. Now, no atmospheric pollution leading to acid rain or greenhouse effect. You see, in the case of a fusion bomb, the damage done by a fusion bomb is not only the tremendous amount of energy released at the time of explosion, but a fission bomb will be harmful for many, many decades to come, because the products of fission are very radioactive, and everything that is surrounding the region will become radioactive. That means if in a region where a fission bomb has been exploded, that region will not be safe for 50 or 100 years because of the presence of that radiation. So a fission bomb is a very dirty bomb. In addition to killing and destroying at the present time, it will keep on killing for many, many years to come due to that destroying radiations of the radioactive materials that are generated during that time. Whereas a fusion bomb, it can be produced, will be a clean bomb. The products will not be radioactive, and also it doesn't produce any greenhouse gases or things like that. There is no waste disposal problems. One of the major problems with fission energy is that the products of fission are very highly radioactive. So the fuel rods that are in a reactor, once those fuel rods are being used and exhausted, you need to remove them. Now, removing them and storing is one of the greatest problems of using nuclear energy, because those materials are very highly radioactive. Where are we going to store them? Now, will you be happy if those materials are stored in your backyard? Well, there are places in the United States where hundreds of millions of tons of these radioactive waste materials are stored. Well, some of them in the mountainous regions of Nevada. Well, that means if you go near there, well, not quite, because they're all very safely contained within very safe containers. So one of the reasons why nuclear energy is still not a feasible form of energy to solve our energy needs in a large scale is the problem of disposing of the waste materials produced in fission. If fusion can be harnessed, if we can find a way to use fusion energy in a controlled manner, then those problems can be solved. Waste disposal problems are much more minimized in fusion reactions. Well, all these are very important when we consider fusion in place of fission. Well, All these are left for later generations to tackle and see how much we can do with these. Can we produce energy from fusion? And can we solve all our energy problems? Can we solve the greenhouse effect problems? Can we solve the environmental pollution problems? Well, that is all problems that we pass on from generation to generation. It's a challenge for all of you. And I hope I gave you some food for thought about not only the challenges of nuclear energy, but also the perils of nuclear energy. Well, I hope you enjoyed this lesson and enjoyed this course. Well, if you have any questions, please get back to me anytime, and I'll be glad to respond to your questions.